Okay, this is chapter 6 of Earth Science, Volcanoes and Other Igneous Activity. Who doesn't like volcanoes, right? They're pretty cool. A lot of action happening. Let's take a look at what goes on in and around volcanoes. Now, there's different types of volcanic eruptions, and there's different factors that will determine the violence of an eruption. The composition of the magma, the temperature of the magma, is it too hot, too cold? And the dissolved gases are a big one because if you have lots of dissolved gases, you're going to get sometimes much larger explosions. And then the viscosity of the magma, how blocky or runny is it? Um, there are some lavas that flow out. I mean, you can't outrun them. They're super fast, and other ones you could stand there and watch them for an hour before they even get to you. So the viscosity plays a role in like how much area is going to be covered, and especially when it comes to like anybody living around the volcano, what kind of danger they may or may not be in. Now, the viscosity again is how runny or blocky it is, so to speak. The hotter it is, typically the less viscous it is, or the runnier it is. Um, these in some areas, this is a huge problem because these volcanoes can erupt and they flow like water, and it's pretty crazy to watch. In other areas, like I said, there's parts of Hawaii that have, these very slow moving, just kind of like crumbles over. It's like really slow. Um, Now the composition plays a role in how viscous things are. Things like if it has a high amount of silica or what we call rhyolitic lava, a lot of silica, silica is quartz and oxygen. They have a tendency to be much slower. It's a kind of a denser, not denser. That's not the right word. Just they move very slow. And you have low silica or more basaltic lavas that have a tendency to move um, faster. Now, within volcanic rocks are lots of dissolved gases. And in fact, volcanologists, we have one in our apartment, they have instruments that allow you to sort of record the dissolved gases in there in the rock. If you powder it, like pulverize it and powder it and put it in a certain machines, it'll tell you how much water vapor and carbon dioxide excuse me, were in that particular volcanic eruption, which gives you an idea of what type of volcanic eruption it was, if it was one in the distant past. So it's kind of like recreating the volcanic eruption based on the water vapor and obviously the chemistry of the rock itself, the composition. So when the gases get near the surface, they expand. There's less atmospheric pressure and they go like this. So if you have lots of gases in the rock, you have a tendency to get a more explosive volcanic eruption. Now, the dissolved gases provide a force to extrude lava. So again, in a weird way, think of it kind of like shaking up a soda, right? You shake up a soda, you put it through a narrow opening, and what happens? It goes, right? So the violence of an eruption is related to how easily the gases can escape. Now, in Kilauea in Hawaii, Kilauea is a very active volcano, but it's also a very a wide opening. It has a very wide crater and very viscous material. So it doesn't get necessarily those big volcanic eruptions like you might see in other areas of the world. Now, lava flows, basaltic lava flows are more fluid, and there's two different kinds of lavas that we talk about, and these are Hawaiian words. One is called Pahoehoe, which resembles like braids of ropes, and that stuff has a tendency to move a little bit faster. It's the less viscous, excuse me, the less viscous lava. Then you have the other one, which is called Aa, probably called that because when you walked on it, it hurt your feet. It's the blocky, rough, jagged blocks. Again, those are Hawaiian words, pahoehoe and Aa. Now, the gases are 1 to 5% by weight, and it's mainly water vapor and carbon dioxide. So if you get a piece of pumice, for example, maybe you've seen a piece of pumice, it's filled with tiny little holes that used to be filled with gas, and it'll actually float on water. So these gases, the gases that are found in volcanic rocks, play a huge role in determining what type of eruption it is, what's the chemistry and sort of the mode of eruption taking place at any given volcano. And this is one, like I said, kind of think of it like paleovolcanology. If I have these rocks and volcanic rocks, I can look at them, look at their chemistry, look at their volatiles, the gases trapped in them, to determine a volcanic eruption that might have occurred 3, 4 thousand years ago. So it's a way of kind of putting the pieces together by looking at the composition and the gases held within the rocks. Here's a picture of Pahoehoe lava. So it has sort of that ropey look to it. Again, it's sort of the stuff that it moves a lot faster. It kind of runs like a river of lava as opposed to, which you'll see in the next slide, which will be the AA. This is sort of what most people think of when they think of lava, right? I mean, it's just sort of that quintessential lava look. And again, it's called Pahoehoe. It's a Hawaiian word. Here's an AA flow, all right, and those are, uh, in this picture, it's AA flowing over the top of an older Pahoehoe flow. So you can see somewhere in there the chemistry changed a little bit, and you could see the very, very big difference between the AA flow and the Pahoehoe flow. The Pahoehoe flow almost looks silver, doesn't it? And that's just oxidation. But you can see the Pahoehoe flow is very smooth in spots, kind of that ropey, blobby look. And the AA flow is very blocky, the kind of thing you wouldn't want to walk across. It'll tear up your feet or your shoes in a hurry. Now, what the things that are extruded during an eruption are what we call pyroclastic materials. It's everything from the ash, the dust, the pumice. The ash and the dust are the real fine, glassy fragments. The pumice is sort of that frothy lava, like I mentioned, that can float on water. You have lapilli, which is like the walnut size. You have cinders, and then you have the big stuff. The blocks and the bombs. Those are dangerous, but hopefully no one's anywhere near those. But those blocks and bombs could be the size of houses. They can be very, very big chunks that get blown out of volcanoes, depending on how explosive it is. So there's sort of this range based on the particle size, from the smallest being ash up through these blocks and bombs that could be the size of houses and everything in between. So these are just sort of the names that volcanologists use to sort of differentiate the different sized particles coming out of a pyroclastic eruption. Let's look at the anatomy of a volcano. So you can think of a volcano, the classic sort of triangular shape. Well, within there you have sort of the conduit or the pipe, the sort of the plumbing that carries everything in up from underneath from below the earth, right? The gas-rich magma, these pipes and conduits carry the magma up to the surface. When it reaches near the surface, you have things like vents that allow gases and sometimes magma to escape. Those are typically found along the sides or the flanks of the volcano. You have the crater, which is sort of the top of the volcano where, the eruption actually occurs. And those are usually steeped wall depressions at the very top. That's where like the magma pool might be. And then you have what's called a caldera, which is a huge crater, so to speak, that's greater than a kilometer in diameter. So that's just a really big crater, where they call it a caldera. You have parasitic cones, which are like mini volcanoes that can form on the flanks of volcanoes. So if you have a vent that's sort of shooting out the side, sometimes that'll create its own little volcano on the side of it. And then you have fumaroles, which are little vents along the sides and flanks of a volcano, but they only emit gases. So here's a sort of that standard picture. You have lots going on here. You have your magma chamber, which is where it all starts, down in the way down deep in the earth. You have the plumbing that brings um, brings the magma to the surface. I'm going to use yellow since this is already red. And then you have things like these are vents and parasitic cones, things that form along the side here. You have the crater at the top here, obviously. You have lava that flows down the sides. Then up here you have the ash cloud. This is the finest particles, and it kind of rains down. This what we call pyroclastic. And if they get really big, if it's really explosive, you get things like bombs. These huge pieces. You don't want to be anywhere near when that happens. Okay. And you can see within the structure of this, you see these sort of these layers in here because a volcano starts as something small and erupts and erupts. And over time, it just builds itself up to these monstrous structures. And that's exactly what happened in Hawaii. Hawaii sits on a hot spot. So over millions of years, it started at the bottom of the ocean as this sort of fissure, just a little area. And as the volcano got bigger and bigger and bigger, eventually it gets above sea level. So right now, the newest volcanic island of Hawaii is being formed off the coast of the Big Island. I always forget what it's called, but in several million years, that'll breach the surface of the ocean as well, and you'll have a new Hawaiian island. Now, there's several kinds of volcanoes. All right, the first one being a shield volcano, which is very low. All right, it's not really steep. It's a very low-looking volcano, kind of like Mauna Loa in Hawaii is the best example of that. It could be tall. It just doesn't have the steep sides. It's very broad um, type of structure. That doesn't make it any less of a volcano. Mauna Loa has been actively erupting for years and years and years. But it just doesn't have that sort of steep nature. And a lot of that is the composition of the magma is much runnier. It doesn't allow for those steep sides to be built because it just runs off. It's much runnier type of magma. You have what's called a cinder cone. All right, cinder cone are these sort of standalone volcanoes that typically occur around a much larger volcano. In my GIS class, we look at cinder cones around in northern Arizona. The main volcano there is called San Francisco Peak, and then there's just a zillion little volcanoes, and that's what one of those is right there. That's SP Crater near Flagstaff, Arizona. They're big compared to a human, but in terms of a volcano, cinder cones are very, very small. They have steep sides, and they usually, like I said, occur in big groups. And they're kind of one and done. So usually it'll erupt once and then it's kind of done. It doesn't keep erupting like a main volcano will. Then you have what's called a composite or a stratovolcano. And these are the ones you kind of typically think of in terms of volcanoes like Mount Rainier or Mount Fuji in Japan. They're large, they have, the steeper sides. Um, they're typically, a lot of them are snow capped, and they have those interbedded lava and pyroclastics, and they typically form much more violently than sort of those very low shield volcanoes do. So these are the ones that probably pose the most risk to humans um, because of that explosive nature. Now, there's lots of volcanic hazards, obviously. Um, what we call this term isn't used too much anymore, but it's called nue ardente, and it's what that is it's a fiery pyroclastic flow made of hot gases infused with ash. So it's not solid necessarily. It's mostly hot, superheated hot gases with gas, and they can flow up to 125 miles an hour down the side of a volcano. And if you go back and read about Pompeii and Italy, you see there people like they're, basically frozen in time. That part of that was the Nue Ardente that just came down the side of the mountain, basically incinerated people instantly because they were superheated and they were entombed in the ash almost instantly. It's kind of scary. The other half of that is what's called a lahar, many of these volcanoes are snow capped. So when they blow their top, so to speak, you have all this superheated magma and lava coming out. And then obviously that comes out on the snow melts. Now you have a combination of volcanic pyroclastic material with water, which leads you to this volcanic mud flow. And these are seriously dangerous. And if they flow like rivers, but they're much thicker and they take everything with them. Houses, cars, it doesn't matter. Anything getting caught in a lahar is going to go with it, and they travel extremely fast. Not 125 miles an hour fast, but very fast. So you can have volcanic ash, which is a serious issue, especially for air travel. So anytime there's a volcanic eruption, especially like in Alaska, like the Aleutian Islands in Alaska, a lot of the trans-Pacific airline routes go over Alaska, and there's to save time because we live on a round ball. It's actually shorter to go over the poles. Well, when these big volcanoes erupt and they emit all this ash, planes can't fly anywhere near that because that ash, if it gets into the engines, will literally stop the engine. And that there have been airline crashes many years ago, where the airplane didn't know it occurred. It wasn't flew right through an ash cloud. Both engines seized and the plane crashed. So that's something definitely you got to be careful of, is with the ash cloud. And you could see that middle image of that house being completely covered. Obviously you don't want that. And then the bottom image is kind of a classic image of Hawaii with the lava flow just kind of flowing right down the street, so to speak. That's an flow, so it's not flowing real fast, but you wouldn't want to stay there much longer. You got to remember that's molten rock. That's like 20 some hundred degrees. It's very hot. Pyroclastic flows, again, is a combination of all of the different size particles that can come out, but they're coming out in an explosive fashion. And when Mount St. Helens erupted back in 1980, that was one of the things. And I remember that it was near my birthday. Um, it was moving at speeds of about 60 miles an hour and sometimes reaching temperatures of 800 degrees. So anything in their way, um, just either incinerated or obliterated, one of the two. Very dangerous stuff. So here's what the lahar looks like, and you can see that person circled here. I'm going to circle him myself here just so I can um, show you. But this is a person standing there. That lahar, I remember seeing footage of that, just carrying away houses and cars and entire forests. It was scary to watch. Very scary to watch. Now, the other landforms created from volcanoes are things like calderas, which is the crater at the top, steep wall depression. They form by collapse, so they get so steep they collapse in on themselves and they collapse in. They're usually pretty circular, and a caldera is one that exceeds a kilometer in diameter. So some of these volcanoes at the top are very big. You don't get an appreciation for them when you're taking a picture from way far back, but those things are huge. Some of those calderas are massive. So here's Crater Lake Caldera in Oregon, and that has a lake with an island in it. So what happens is you have some volcanic activity here. I'm going to look at my other screen here. So you have some activity over here, and it creates some volcanic eruptions, and eventually the summit of that volcano collapses in on itself. It kind of breaks down and comes back based on faulting. You got to remember, this is an explosively nature, it's coming out. It creates rock cracks in the rock, and those rocks just sort of come back in on themselves because of the sheer weight of them on these cracks, what we would call faults. And you could kind of see those in there a little bit. And here they all cave in back in on themselves, and then eventually it fills with water, either because it reaches the groundwater level, or it fills with rainwater. And so that's how you got the Crater Lake. I've never been there. I would love to see that. I'd like to go out to Wizard Island, But that is a that's Crater Lake is a caldera. It used to be an active volcano, and it could be again someday. You never know. You have other volcanic landforms like fissures, which are sort of linear in fashion. You can see that up here in this top image. Looks that's sort of that whole thing where the earth is cracking open, and you see that in movies a lot. You actually don't see this type of thing very often. It does happen. Um, and then you can see as it opens up, the basaltic flows go out in each direction. Here's sort of an example. This lower image is an example of what would look like from the air. And these, there's some massive amounts of these out in the west coast. They're ancient in age, so to speak. They happened a long time ago, but the entire, thousands of square miles are covered with some of these. The Columbia Plateau is one of those areas out in Oregon and Washington, Idaho, and northeast, or excuse me, northwest Nevada. That whole area is covered with these sort of shield basalts, massive volcanic eruptions that just spread basalt out over large, large areas. Now, this happened millions of years ago, though. Here's the Columbia River basalts. Again, they covered quite a bit of area. Um, so to give you a rough size scale, this is the area that the ash from Mount St. Helens covered. Here's the some of the eruptions from a long, long time ago. You know, that if they occurred when they occurred, they covered much of the entire middle of the country. So you can see there's some huge area here. So yes, Yellowstone is a hot spot, and if that thing were to ever decide to blow again, much of the country would be in a world of hurt. It would do some serious damage. Here in Wisconsin, we'd be directly downwind of that, and it would turn summer into winter in a hurry. You have volcanic pipes and necks, and you've probably all seen this before. A volcanic pipe is sort of the plumbing that was stayed intact, but the volcano around it is gone. And a volcanic neck is like in Shiprock, that these are vents left standing, like I said, after the volcanic debris around it, or the volcano itself around it, withered away or eroded away. So let me show you an example of that. So here's Shiprock in New Mexico. I didn't get a chance to see this when I was out there. It wasn't too far from us, but so the idea is at one time you had this volcano that surrounded this inner tube. This is and that inner rock material is much more resistant to erosion. So over time, that all eroded away. All this stuff just eroded away, leaving behind a part of the neck. Now, that's no small part. I mean, it's still 1,700 feet tall, but at one time it could have been two, three times that size. It's just that's what it's eroded down to. So if you see something like this, and Shiprock's one of the most famous examples, along with Devil's Tower in Wyoming, because the terrain around there is so flat, this thing just sticks up out of nowhere. It just comes up out of nowhere, and it's pretty interesting that way. But again, what that is that's you're looking at the internal plumbing of a volcano with the rest of the volcano having been eroded away. When you watch lava come out of a volcano, it's pretty neat, right? You see all this molten rock come out. The thing is that most volcano material, the magma, is actually emplaced or cooled within the earth itself, and we call that a pluton. So these are underground igneous bodies that you don't see at all unless if the material above it has been eroded away. Now, there's two kinds of shape for this. There's the tabular or sheet-like plutons, and then there's sort of the massive plutons. We'll take a look at those. So let's look at some igneous intrusive features, and you might have heard of some of these. There's a dike. That's a tabular discordant pluton, so that means it's going across layers. Okay, it's cutting across layers. You have a sill, which is a concordant pluton, which goes along layers. And you'll see that in a diagram in a second. Um, and then you have a laccolith, which is very similar to a sill. Let me show you an example of these. Okay, so let's look at some intrusive igneous bodies. I'm going to look at my other screen just so I can read this. You have what the cinder cones sitting out here. These are sort of by themselves here. Little. You have the main composite cone, which is where the bulk of the heat is. You have what's called a laccolith, which is kind of a lens, if you will, a lens of molten material that's underneath the ground. You have dikes, which go across. Okay, so they cut across like this. They cut across the layers. And then you have sills, which form right along those layers. It's a little harder to read, but think of those as parallel to the layers. Now, if you look down here underneath this diagram, you can see that the magma chamber kind of bounces around. Okay, so the magma chamber, there might be multiple magma chambers. So here's one over here that's kind of contributing to the laccolith. Then you have the main one that's underneath the main volcano. And you might have some ancillary ones that create fissures and things like that. Now, when the magmatic activity is all done, everything that gets all of that magma in the ground solidifies. So what happens to that is it becomes what we call a pluton. So now you have all of this molten material that is now rock. All right, it's all solidified. And when that becomes, when everything erodes down to its level, you get what's called a batholith. So all of this material up here, if you come back up here, all this material here, all of this over millions of years gets eroded away, and you start to see essentially the top of this eroded material, which is now called a batholith. And you can see that these batholiths out here in I believe this is Yosemite National Park in California. Here's a sill out in Utah, and you can see it's a layer that's in the same direction or parallel to all the layers below or above it. So it's just sort of in a way, the way I always remember sills is they're sort of injected into the rock in terms of it's right along the layer and it's parallel to those layers. It's sort of injected into it. And then you have a dike here, which is because this is basaltic material, you'll notice that it's sort of raised up. It looks like it's raised up. And what that really is that it's more resistant to erosion and everything else around it has eroded down to that sill. So it actually kind of sticks up. But this cuts right across all of the rest of the geology. So that's what a dike is. So we already saw some images of the intrusive features. I mentioned that a laccolith is sort of this lens shape, massive molten material that then hardens. You have batholiths, which is the largest intrusive body, and curves. That's where you have all of those magma pools underneath the ground. They kind of change, but over time they all solidify, and then everything gets eroded down to it. And those could be really, really huge, hundreds of square miles or kilometers, excuse me. So here's some examples of some here's a laccolith in a sketch here. So that's this right here, this black lens shaped thing. Here's the stock. And then you could see it. It's a little harder to see in the picture actually than it is um, in the diagram. But you can see this dike right here cuts straight across. You can see it cuts straight across all the layering, and the sill kind of gets injected in between the layers. The magma originates when you have solid rock at depth that is then melted because of the enormous amount of heat that comes up from the upper mantle. Now, there's different factors that play a role in the generation of magma. And as you go deeper in the earth, it gets hotter and hotter and hotter. However, you just in the upper mantle alone, it's not necessarily hot enough to melt rock. So you have to have some help from even deeper. You have to have this sort of magma pool that comes up and starts to touch the rock underneath, and then eventually melts it. And then the heat rises, and that heat, the magma rises up to the surface of the earth. So you have to have several things going on here. You have to have the hottest part of the upper or lower mantle coming up, welling up in some type of convection current towards the surface to melt the rocks that then create the earth, the volcanoes. Here's a chart showing you the geothermal gradient of the earth. So as you go deeper into the earth gets hotter and there's more pressure. And it actually takes, you have to get pretty deep before you start getting partially melted rock or completely melted rock. And if you look at this, you can see that at 200 meters, okay, right here is the geothermal gradient. All the way out here is where you finally start getting, you have to have like almost 1500 degrees Celsius to start even partially melting. And everything is solid in this green section and then partially melted in the orange section. And then you really got to get deep before you start getting into completely molten. And that's where the only way to achieve this is if you have material from below that's already melted coming up. Because at 500 kilometers, you would have to be, it would have to be all the way at, well, let's see here, 2200 degrees Celsius before the rock starts to melt. That's just not feasible. That's not where the Earth gradient is. That's what this red line is. This red line is kind of where the Earth is now. So in order to get out here, way out here, and melt this down here, you have to have help from below. So how do you get that? You get friction from subduction zones. You get crustal blocks heated during subduction. So we talked about that when the one plate's going down beneath another, that rock is being pushed way down deep into the upper mantle, and that's where you start to get melting occurring. That melting causes the rock to be buoyant and come up in the form of volcanoes. That's why we have volcanic arcs at the edges of the plates, or you have rising hot mantle rocks like in a hot spot, right? That hot spot is relatively stationary. It's just burning a hole through the crust because it's bringing up these superheated, already melted rocks that are then burning the rocks above it. So it goes way, way deep. You can't just melt rocks, as you saw in that image, at 500 kilometers. The rock is still solid at 500 kilometers. Even though the temperature is high, so is the pressure. So you have to have a combination of a lot of heat already down there coming up, and then the thinning, high. You have to have abnormally high pressures and temperatures. Now, how does pressure play a role in there? Well, as you go deeper, the confining pressure causes an increase in melting temperature. If you've ever used a pressure cooker, that's the whole principle. By putting the lid on a cook vessel that allows you to boil it, let's say if I put water in a pressure cooker and I snap the lid on tight, the reason why things cook faster is because I'm holding in all of that pressure, which allows the water to boil at a higher temperature. So by putting the lid on it, keeping it, this is, by the way, how they make Kentucky Fried Chicken as well. So they're pressure cooking the chicken to allow the grease to get to a higher temperature, make it crispy, but not take as long to cook. Because otherwise, chicken would take forever to cook, and it would end up being burnt. Um, so you you having a high pressure at depth, which is what happens as you go deeper, also means that it's going to require a higher temperature to melt those rocks. So that's why any type of drop in confining pressure can cause decompression melting, and that occurs typically with subduction zones. So as the slab is going down into the earth, it's releasing that pressure as it goes down in there, allowing those rocks in the descending slab to melt enough to create the volcanoes above it. So let's have an example of decompression melting. And this sort of will hopefully help you understand that whole geothermal gradient and how it needs help from below. So you can see in this image, I'm going to look at my screen a lot. You can see in this image we have a mid-ocean ridge, and here we have a magma chamber right here that's creating heat from below. It's driving the plates apart. New Earth is being created. Well, how does that work? That magma chamber alone has to have fuel. It has to have something that's keeping it lit, so to speak. Well, that's this. That's where you have this bubble of even hotter rocks coming up from a hotter part of the earth and sort of keeping the fire stoked, if you will, for this magma chamber that's then forcing the magma to come up through the oceanic ridge. And this same thing occurs in this subduction zone as well. Another huge role in how magma is formed are the role of volatiles, or the gases that are found in the rock, primarily water. Um, what that does is if the rock is saturated with water, so to speak, it causes the temperature at which it's going to melt to lower a little bit. And so this is how subduction plates are able to melt at deep depths. They're soaked. They've been sitting at the bottom of the ocean for millions of years. They're waterlogged essentially, which then lowers that um, that melting temperature. Even though the pressures are getting greater, the water brings down the melting temperature, allowing it to cause it to melt and then create the volcanoes. So here's an example of that. So we have a plate going down into the earth, one subducting under another. Once it reaches sort of that critical temperature, the water in the rock um, causes partial melting, allows it to cause partial melting because the water lowers that temperature again, causes partial melting that rises, creating sort of either a pluton or a magma chamber, which then creates volcanoes. So then as the plate moves, you could see these remnant ones. So there one used to be one here, then there used to be one here, now there's one here. So they kind of move around and you get these chains of volcanoes that run in an arc, so to speak, along the same as the trench because this is being melted down here. It goes down, it creates a volcano, then it moves some more, creates another volcano, similar to a hot spot, but not quite the same dynamics. These form in a chain because this trench goes back in this direction as well. So this melting is occurring all the way back here in this direction as well. So you get these chains of volcanoes. The Andes Mountains is a good example. The Aleutian Islands in Alaska is a great example of these arcs, volcanic arcs created by one plate being subducted beneath another. But it all starts down here with the subducting slab having excess amount of water, lowering the temperature at which it's able to start partially melting. Another factor that goes into how magma is formed, it has to do with when it is partially melted. The igneous rocks themselves are mixtures of minerals, and that melting occurs over different ranges of temperature. Some minerals melt faster at lower temperatures than others. So the ones that melt at lower temperatures are sometimes converted into something else that might produce a magma with a higher silica content than the original rock. Now, most basalts have low silica in them, but there's other things in the rock that'll allow that silica level to rise based upon the chemistry. Where these volcanoes are formed is not random. They're located typically at the margins of ocean plates, especially, like I said, where one plate is subducting beneath another. The other one is confined to the deep ocean basins where you have the mid-ocean ridges being pulled apart. And then there's a few that are found within the interiors of the continents. So you've probably heard the term ring of fire, and that's where the bulk majority of the volcanism on Earth takes place. So you have the Andes Mountains, you have volcanoes throughout Central America, Then it kind of skips. This here is not. This is a transform fault through California, the San Andreas. But then you have the Cascade Range with Mount Rainier, Mount St. Helens. You have the Aleutian Island Arc here, all the way into Alaska. You have the Russia, Japan down into the Marianas. You have the Tonga, New Zealand area. So you can see there, and there's more. This is where the Ring of Fire is and where the bulk of the volcanism is taking place at the surface of the Earth, but also in the ocean as well. So plate motions provide the mechanism by which mantle rocks melt to form magma. And we talked about this already. When you have one plate slowly descending into the other, eventually the water in the plate lowers that temperature, which allows it to partially melt. Then that rises upward, creating some type of volcanic form, whether it be a volcano or mid-ocean ridge or something like that, volcanic arcs. So you see this pattern now that you can kind of hopefully start to understand that the magma is dictated by obviously temperature, pressure, and then water content or volatiles. Here's that convergent boundary like we've already seen. You have one plate diving down here, starts to partially melt, creates a volcano here, and then goes back in that direction. And it's not just one volcano, it's a whole string of them. Divergent plate boundaries, we've already seen this, where you have the upwelling of the magma, the plates are being pulled apart, new earth is being created, and then you get these basalts that are formed down in the deep ocean ridges. And you can see that here. So this gets welled up here, it flows out to that side, flows out to that side, driving the plates apart. The best place to see, one of the best places to understand how this is taking place is in Iceland, because in Iceland, this is actually occurring at the surface. In most places, these divergent plate boundaries are in the ocean, but in Iceland is actually come to the surface. I believe, yeah, that's a picture of Iceland right there. So all the volcanoes and geysers and all of the other igneous type of landforms in Iceland are there because Iceland sits right on this mid-ocean ridge and is actively being pulled apart. Now you also have what's called intraplate activity, where you have hot mantle plumes. And we talked about this. This is hot spots, right? The Hawaiian Islands are the best example of that. But you also have Yellowstone, or what they call the Columbia River Plateau. Um, but Hawaii is the best example of that, where you have this sort of consistent point of heat below the surface that continuously burns holes through the crust. So we have this partially melting that kind of comes straight up, then the plate moves in that direction, creates the next island, plate keeps moving in that direction, and you could see that. So the plate comes up, plate moves, new one comes up, a new one comes up. So you have all of this island chain because this hot spot is sort of persistent in one spot and it just burns a hole through the crust. Okay, so that's chapter 6. It's a bit of a quick chapter. I know I'm talking very fast. Hopefully you got something out of that combined with the book. There's a lot more in the book. I like to give you the lectures. It helps me to kind of interact a little bit with you all. But that's it for chapter 6, and I'll see you on the next one. Take care. Bye.